Okay, welcome to this tutorial. Today we are going to talk about importing data and being able to consider a non-uniform velocity inlet. So up until now, as you recall, we've discussed only a uniform velocity. In other words, we need one number to define the inlet velocity. In reality, if we're comparing to experimental data, then hopefully we have velocity measurements, we have turbulent kinetic energy measurements, we have a way to estimate dissipation profiles. And so these inlet quantities are very rarely going to be a single number. So how do we account for the fact that it's a profile as opposed to some uniform profile? Here is a possible function that could describe the inlet velocity. We'll talk about how to take a measured data and interpolate to the discrete values that are the inlet cells faces. Because in reality we need to take the discrete values, the x and y values there, and then evaluate a function that describes our profile at those key locations, at those discrete locations, or we need to take experimental data, which undoubtedly is going to be measured at different intervals and at different locations than the XY locations that we happen to have for all of our cells. So we need to be able to take that and interpolate that to the base X and Y locations that represent our inlet cells. So the function that you see here on this slide is a way of approximating, not a very good way, mind you, but for the intents and purposes of what we're trying to do here, this will be perfectly fine. We have something that's similar to a turbulent profile. In fact, as this 4 goes to infinity, then we have a top hat profile. But the origin here is at the corner. We are shifting it by 0.05, so half of the length, width and height in both x and y directions. And this 0.064 in the denominator, this constant out in front, this enables us to express this in terms of the average velocity instead of the peak velocity. And you find that for us, everything we've done so far, this is just 1 meter per second, so we'll leave this as 1. So if you integrate this function from 0 to 0.1 in the x and y, then you'll find that the average here is going to be this UZ average here. And this is only true for an exponent of 4. If you change this to 6 or 10 or 12, then this number is going to change a bit. And as it goes to infinity, then this obviously goes to 1 because the coefficient out in front is our maximum velocity, but it's also since it's uniform, it is the average velocity. Okay, so for an exponent of 4, we got this 0.64 out in front, and this is what we're going to use. This is what the profile would look like if we had hundreds of measurements in both x and y. So what we're going to do first is assume that we have some function that defines the profile, and we're going to apply that in our U file for the most recent time that is going to be used for the simulation. Okay, so let's go to, I'm going to copy over this channel, this case 7. And we'll go into this new folder that I just called test and clean it up a little bit. Okay, so I've got a 0 folder, I've got a 332 folder. I could actually remove the 0 folder. I want to keep the 332 folder because that's going to be the internal velocity field that is going to be somewhat accurate. Presumably this is a converged solution from some other simulation, and we want to be able to use that for the as the initialized field. So if I go into this folder, then I've got my epsilon k, my viscosity, and my pressure and my velocity. So we're going to leave all these other ones as uniform profiles for their inlets, but let's just worry about velocity. The concept can be applied to any of the other ones if we happen to have profile measurements for them as well. So if we take a look at this U file, it's a 15 by 15 by, I think it was 600, so yeah, 135,000 elements internally. And if we scroll all the way to the bottom, we see the boundary files. You notice that each one of these entries is a 3-component velocity vector, so the x, y, and z. And this list here, the internal field, and it says non-uniform list, and it specifies what type of numbers this are. If you might see a scalar, this happens to be a vector, and then it lists the number of elements that then occur after in the list. And there's an open parenthesis, and if we scroll all the way to the bottom, we've got our boundary field inputs, but the remainder of these internal fields, we have the close parenthesis and a semicolon, and then we jump into the boundary field. So the inlet right now, again, is a uniform velocity, but we basically want to change it to be something similar to what's shown up here for the internal field. We're not going to have that many elements. We're only going to have 15 by 15, so we should only have 225 elements. But the format of the list is going to be the same, and we can approach this a number of different ways. There is some functionality within openFOAM that you can map the fields. I find that that's problematic at times, and I typically just do this outside openFOAM, so that's what I'm going to demonstrate today. But just keep in mind what the format of this list needs to look like. Okay, so we're going to copy this much over, or copy this much down to the inlet. So we're going to have a non-uniform list. We're not going to have this many elements. We should have 225. And then we'll close our parenthesis and then end with a semicolon. And this open bracket, this closed bracket is tied to this open bracket. Okay, so I'm going to save that. And the outlets can remain the same at 0 gradient, and the fixed walls obviously are going to be no slip still, so we don't need to change any of those. We just need now to list 225 3-element vectors that are tied to the x and y locations of the cells that define the inlet surface. So in order to find those, we're going to run a function out here called write cell centers. Notice it is a center with an RE. This means that the utility was written by someone with the British way of spelling the word center. Notice if I tried ERS, the command is not found, so I have to be careful to use the spelling that the utility uses. And if I hit enter, it's going to go through each of my time directories that I have. I only have one there right now, the time directory 332. And it's going to create some new files within that directory, CCX, CCY, and CCZ. And then the volumes, I'm going to have another file of this capital V where the volumes and the face areas are located. I'm not gonna need to use that one, but I will use these other ones. So if we take a look at CCX, for example, the format is similar to what we just saw for the U, but we've got non-uniform list, and this time it's a scalar instead of a vector, and it has the same number, which is not surprising, same number of internal elements. And if we scroll all the way down to the inlet, then you'll see that there's 225 X locations for all the inlet data, or all the inlet cells. And we're going to go into the CCY file and get the Y locations for each of those elements. The Z location is not needed because they should all be Z equals 0. You can go in there and verify it if you'd like. But you can see that for the first 15 elements, it's the same X value, and then it steps up some amount and goes to the next, in this case, the next column. So this is going column by column, the first column, the second column, third column. If we take a look at the same entries in the Y, then you find that there is it will be stepping up in Y from 0 to some maximum, and then 0 to some maximum. Okay, so really all we want are these files here. And again, I'm going to be doing this outside of openFOAM. And so I'm going to make a file called inlet X. I'm going to paste these. I'm going to paste the values that I just copied over. Oh, I copied way too many of them, didn't we? Oh, we copied inlet and outlet. So all we really need are these 225 right here. And we'll do the same thing for CCY. First, let's make a inlet Y file. And I'm just going to go grab all these. And you'll see that they are stepping up and then repeating. So we have 225. This is just a text file with 225 elements for the Y and 225 elements for the X. And now we can take our function and evaluate it at each of those X and Y locations and create another file that has the resulting velocity. So in order to do this, I am going to use Octave, which is similar to MATLAB, if any of you are familiar with MATLAB. See, I need to get my function. This was, first of all, I'm going to load, I'm going to create a variable called X, and I'm going to load the inlet x file. I'm going to do the same thing for y. And if I plot x versus y, you'll see that the font size isn't real big there, but you get the picture. So we have x is constant, we step up in the y, and then we go to a new x, step up in the y, and so on and so forth till we map that entire inlet surface. So now I've got a vector in my workspace, in my Octave workspace, a vector x and a vector y, and now I just need to create a velocity vector in the z direction, and using my function, then I can call this uz equals 1 minus x subtract 0.05 divided by 0.05 We're going to square that or raise that to the 4th power, and then multiply that by, I didn't need a parenthesis there, did I? Needed it here. And multiply that by the same thing in the y direction. Raise that to the 4th power, close our parenthesis, close the entire parenthesis. We're going to multiply that by 1 divided by 0.64. And again, I'm getting this from here. I'm basically just building this equation into my Octave. And I already have the x and the y locations of the cells loaded, so I can just hit enter. This is going to give me an error because same thing in MATLAB, right? It's using these vectors, and if I try to take a vector and raise it to the 4th power, it's thinking it's a matrix. You can't raise a non-square matrix to the 4th power. So I've got to come in here and put periods next to these. I'm going to have to put one here too when I multiply them through, and that should do it. Okay, so I could take a look at the UZ just to verify that it is correct, and for the most part that looks good. So here's my x and my y, and my z has some, it's not a parabolic profile, but it's a 4th order profile, and this is the function we are modeling. So now I've got x, I've got y, I've got uz. Now I need to create a file that has my 3 components of velocity in there. And I need to have, if you recall the u files, when it's listing each vector and each line, then it's got 3 components, and then they're separated by spaces, and they have 2 enclosing parentheses on each line. So in order to do this, I'm actually going to open up another terminal and create a file. We'll call this inlet U for inlet velocity. And I'm going to open this file. And I'm going to specify that I'll be writing to it. And then I just need to do an fprintf. And we'll list the file we just opened. And we're going to need three. Well, we're going to need a open parenthesis, and then we'll need 3 values in here. We'll have 8 digits and 4 past the decimal point. And then we will close our parenthesis and then have a character return for the next line. And then we are going to this is going to be our X component, our Y component, and our Z component. And since our streamwise direction is in the Z direction, we will just put 0, 0, and Z in this case. Actually, we gotta go back here, and we're going to define a variable n, which is the length of x, which is 225. And now we're just going to make a loop for I equals 1 to n. And then here's where we're going to do the fprintf. ID, and then our open parenthesis, we will do 8.4f, 8.4f. We'll close our parenthesis, and then we will have a character return. And here is where we will put 0 for the x, 0 for the y, and then for z, we will just put uz of I, since that is the loop that we're stepping through. So we've got our index that's going to step from 1 to 225, and it's going to print the uz in that third component for each line. And then we'll end the for loop, and we will close our file. And then we can exit Octave. We're back into our terminal window. So let's go ahead and take a look at the inlet U file. And you can see that we've got 225, hopefully, 225 lines in here. And my x component is velocity is 0, my y is 0, and then here is my z, which is defined according to the function that I had and is tied to all the x and y locations for the cells for the velocity. So now what I have to do, I got to open that back up actually, and we'll copy that, and we'll come into our velocity vector, and we're just going to paste it right in here. We've got 225, open parenthesis, close parenthesis, and semicolon. Now we save that. And we should be ready to start the simulation. This was a standard k-epsilon model, so we should be able to actually, let's open up ParaFOAM real quick, ParaView. Oh, I needed that 0. Okay, so let me copy. Okay, so now I've got my 0 folder. Now ParaView should hopefully work just fine. Okay, so we've got our 0, which since we just copied it over, the velocity, the inlet velocity, I'm gonna change this from the internal mesh just to the inlet, so we can take a look at the inlet by itself. If we look at the surface with the edges, then we've got our 15 by 15 array of elements. And if I go to velocity here, this is going to be a uniform velocity because I just copied over that 0 folder from the other case. But if I come here to the first step, then we've got some problems in here. Let's go to the inlet, line 135031. And this is likely occurring right where we pasted everything in. We got boundary filled, inlet, non-uniform list vector. Oh, we forgot this. We got to, we deleted too much when we modified the original file. We still need to have type, fixed value, and then value. And in place of this uniform is where we'll have that non-uniform vector. So we open with the bracket, and we need the type, fixed value, and in place of this uniform, we will have a non-uniform list, and this list is a vector, has 225, open parenthesis, close parenthesis, the semicolon, and the closed bracket. So this should be good to go. If we open up parafoam, and it loaded just fine, I'm going to go to the inlet patch. And if I move to velocity over here, then we see the profile that we calculated. We found from the when we created the file in Octave. And so you can do this in MATLAB or really any other one of many different software packages. There are some functions to map the fields, for instance, in openFOAM, but again, I find it to be troublesome at times, and so I prefer to do it outside of openFOAM. And if we go to the 0 step, then it's a uniform because we obviously hadn't changed that yet. We don't need to change that here. We could just simply run simple foam at this stage, and it's going to start at time 332, and this new, I'm not going to run it, but this new simulation is going to take that inlet data of that profile, the non-uniform profile. So the question is, how do you handle it if it's not a function, for instance, if you just have a set of data and we need to interpolate to the cell values now. If you're going to use Octave like I did here, then you're going to want to use the function grid data, which can take two vectors and a velocity or some profile of something else like kinetic energy, for example. And then you tell it which points you want to interpolate to. You can specify whether it's a linear interpolation, a cubic interpolation, nearest neighbor, I think, or some other options as well. MATLAB has similar functions, scattered interpolant, but it's really up to you using a software of choice to build that file, but the process is the same as what we just went through here. So that's how you take a non-uniform profile of something and build it into your simulation. So the velocity is obviously a vector. If we were going to build a profile of kinetic energy, then that's going to be non-uniform scalar instead of vector. And if we are going to build Reynolds stresses in there, then it's going to be non-uniform instead of scalar and vector is going to be tensor, symmetric tensor. So you can go back to any of the R files that we created, and you can take a look at the format of those. Okay, so this concludes the tutorial for non-uniform profile, and thank you.